Linear models, chapter 3, section 1. There are several models here that we'll talk about. Let me begin with this one, and then we'll move on. A model is no more than taking some kind of mathematical equation or formula and then just applying that to an application, to a real situation. So number 3, just to like an appetizer to get ourselves together and to get ready. The population of a town, we're going to use that that equation up there for growth. Decay, you remember, you put a negative in front of the k, but for growth, dx over dt or dp over dt equal to k times p, if you will. The population of a town grows at a rate proportional to the population present at time p. So I'm going to write that as dp over dt is equal to k times p. On one of the problems on the test, you had to derive that, right? So I'm not going to work that. I still want you to go and do that if you didn't do that. But the formula that you get, that, remember, I spent time and labor in doing that in class for you. So here, the population is equal to some constant times e to the kt. So it says the initial population of 500. So that simply means that when t is equal to 0, the population is equal to 500. It says that in 10 years, when t is equal to 10, the population increases by 15%. So this is 500 times 0.15 plus 500, and that gives us 575. So in 10 years, the population increases to 575. Let's stop there and solve for this constant c and also the constant of proportionality k. So we start with the first initial condition. When time is equal to 0, the population is 500. So we have, 500 is equal to c times e to the t is 0, so just e to the 0 times k, but it's still 0. So that implies that c is equal to 500. So we have p is equal to 500 times e to the kt. Now if we let t equal to 10, p equal to 575, we can solve for k. And this implies that 575 is equal to 500 times e to the 10 times k. Divide both sides by 500, then take the natural log of both sides, then divide by 10. Can we do all that in one step? I don't know. Okay. So anyway, 575 over 500 is equal to e to the 10k. Take the natural log of both sides. Is equal to 10k. So k is equal to the natural log of 575 over 500 divided by 10. So what do you get there for K? Okay. Okay. And so if that be the case, then we have P is equal to 500 times e to the 0.0139 times t. So then the question is, what will the population, what will be the population in 30 years? So when t is equal to 30, we solve for p. So at t equal to 30, this implies that p is equal to 500 times e to the 0.0139 times 30. And that gives us it's about 500 and what, about 70 something? So 500 and, was it 70? What was the rest of that? Seven, that's what I meant, I'm sorry. Yep, 760. Point something, right? 0.4 something, whatever. Okay. So this is fine. Okay. Any questions there? Yes, sir. Mm-hmm. No. That's number 2 from the test, right? That's what I want you to go back and do yourself. Right? I did that in class. Do you remember? Okay, I did that in class. I want you to go back and you can look that up. My 8th grade teacher told us that some things you got to dig for yourself. He said, if I give you everything and you don't do any digging, you won't appreciate it. He said, but if you dig it, it'll stick to you. A little boy knocked on a man's front door one morning and said, "Mister, can I have a nickel?" And the old man thought that was just the funniest thing. Reached in his pocket and gave the little boy a nickel. The next day, the little boy came back and said, "Mister, can I have a dime?" And the old man said, "You're getting expensive, lad." Thought it was funny. Still, reached in his pocket and gave the little boy a dime. The third day, the little boy came back and said, "Mister, can I have a quarter?" And the old man said, "Son, come on the back and I got some trash. If you take that trash out for me, I'll give you a quarter." The little boy never came back. See, if society, if the government, whoever it is, if mama and daddy, if they always giving us something, man, there's nothing for me to do. But when I do it myself, you got something. I want you to go dig that. Go look at it yourself, because I can write it down. But it's futile for me because I've been doing it for 35 years. 30 years. I need you to go do it. You got, my professor, he would say to us, kind of wittingly, but it was true. We'll say, "Dr. Maryland, how did you get that right there? And he would say, I just used my pencil. And the young lady would say, sir, and he would say, just use your pencil. Because something happens to the mind and the body and the soul when you do it with your hand. I know I'm right about that. God said to John on the island of Patmos, he said, what you see, write. I see folk coming to class. How come you can come to a linear algebra, or calculus 3, or differential equations class and never write anything? I got to write something, man. Because when you write it, somehow there's something that goes on in the mental mechanics of your mind that helps you to remember it. Write it. Write it. You write it. Okay, anyway. Now, you see that problem number 13? That's the same problem that I have in the syllabus. Probably changed the numbers up. It's still the same exact problem. Okay? Let's just go back. That's number 13 from this section. Now, let's talk about mixture problem. So in this mixture problem, a large sink is filled to capacity with 500 gallons of pure water. So in here we have 500 gallons of water. Brine, containing 2 pounds of salt per gallon is pumped into this tank. So here, this is 2 pounds of this salt mixture is pumped in. And the rate by which it's pumped in is said to be 5 gallons per minute. And then it says the well-mixed solution is then pumped out at the same rate. So the rate here is 5 gallons per minute. So we'll say down here is the rate out. And this is the rate going in. This is find the number or the amount of salt, pounds of salt in the tank at time t. Find A of t the amount of salt. At time t. Well, we can form a differential equation. The differential equation simply says that dA over dt, the rate of the amount of salt at some given time t, is said to be equal to the rate in minus the rate out. So to maintain some kind of steady flow of equilibrium, so what goes in, what comes out, take that difference, and we can find the amount of salt that remains within the tank. Now let's look at the rate in. That'll be easier to capture first. So the rate in is equal to this 2 pounds, I'm just going to write it over the gallons times the 5 gallons per minute. So the quantity of the gallons would cancel. So here the rate is 10 pounds per minute. So the rate out has to be confined to that same ratio, right? Some pounds per minute. So the rate out is equal to, well, I know that there are 500 gallons of water in this that's going to be mixed with this salt mixture, but in terms of what's the amount of salt, that's what we're looking for. Well, the amount of salt is said to be A, right? The amount of salt at time A. So this amount of salt is in pounds. So here I have A, the amount of salt, I'm just going to say parenthetically, that's in pounds, divided by 500 gallons. It said that the rate by which this mixture is being pumped in is the same rate as it's coming out, right? So here that rate is 5 gallons per minute. So that gives us A pounds over 100 gallons. So here this is A over 100, and the units there is pounds per minute, excuse me, the gallons canceled out. So now we can form the differential equation. Remember that dA over dt is equal to the rate in minus the rate out. So here we have dA over dt is equal to the rate in. The rate in gives us 10. Let's just put the numbers there. And then this is minus A over 100. This implies if I write that with some kind of familiarity to what we've talked about before, let me write this. This is dA over dt plus 1 over 100 times A is equal to 10. What kind of equation is that? Linear, indeed. I wrote that in that way instead of saying A over 100. I wanted you to see that this is of the form, you remember back then we wrote it like dy over d, it was dx, plus p of x times y is equal to some f of x. Generic, right? The y and the x's are generic. They can represent anything. So here, the y represents A and the x represents t. So we need to find the integrating factor. So mu is equal to e to the integral of p of x dx. This is e to the integral of 1 over 100. That's that p of x. Here, this is dt. We got t's and a's now, right? So it's p of t dt. So we integrate this guy. Let u equal to 1 over 100. Let me integrate that first. This is e to the t over 100. And I'll come back to this. We'll need that later in just a second. So I multiplied the left side and the right side by the integrating factor. And the equation that we're looking at is this one here. So remember we said that the left side is the derivative of the product of the integrating factor e to the t over 100 times the dependent variable, which is a, is equal to the right side multiplied times the integrating factor, 10 times e to the t over 100. Is everybody with me on that? Is that okay? We integrate both sides, so that left side just becomes the inside term here. This is just e to the t over 100 times a is equal to 10 times the integral e to the t over 100 dt. So now that's where I need to show the u du. Let u equal to that t over 100, and so du is equal to dt over 100. So 100 du is equal to dt. So the left side stays the same, e to the t over 100 times a is equal to 10 times that dt is being represented by 100 du, right? So this is times 100. It's the integral of e to the u du. So this is just 1,000 times e to the u plus some constant. So 1,000 times e to the u, and that u is t over 100 plus some constant. So let's see what we have. This is e to the t over 100 times a is equal to 1,000 times e to the t over 100 plus c. Divide everything by e to the t over 100, and we can solve for a. This implies that a is equal to 1,000 plus c times e to the negative t over 100. Now the initial condition of the amount of salt that's in there initially is 0. So a of 0 is equal to 0. They're pumping it in, right? What's there initially is the 500 gallons of water, right? So there's no salt initially. So we can use this initial condition to solve for C. So we have 0 is equal to 1,000 plus C times e to the 0. And that implies that C is equal to negative 1,000. So the amount of salt at any time can be found by the equation A of t is equal to, yes, 1,000 minus 1,000 times e to the negative t over 100. So if you want to know the amount of salt at 5 minutes, you just plug in little t to equal 5, and you can solve for the amount of salt. Any questions there? The next problem, a problem on series and circuits. For a series circuit containing only a resistor and an inductor, and we got the image there of what that very simple RL or LR series looks like. It's confined to Kirchhoff's second law, which says that the sum of the voltage drop must be tantamount to the voltage drop on each of the circuits in the series. And so here we only have two of those, and that is the resistor and the inductor. That forms for us a first order linear differential equation. If you add a capacitor, then we have a second order. And we keep on adding terms. We get sometimes not a higher order, but we get a complexity sometimes of that second order. And sometimes we have to go to the third order, but typically we tend to stay around the second order for applications. But here, all I'm requiring for us to investigate today is just this first order. So L is the inductance, and for number 29, that's given by 0.1 Henry. R is the resistance given by 50 ohms, and the voltage is 30 volts. So we just plug in those three terms, we have a first order linear differential equation of which we can solve. So here, this is 0.1 di over dt plus 50 times I is equal to 30. Now, we remember that Ohm's law tells us that this voltage should give us, in the long scheme of things, so-called the current times the resistance. So we'll know what we're working with if we have to solve a differential equation. And I want you to see how in the differential equation, it has the limiting process. Once you take the limit of this current, you get Ohm's law. And that's all he did. He just used calculus on the equation, and he got the result. He said the result is where circuits tend to end up with. That's what you want. So let's look at this dE. So this is 1 over 10 times di over dt plus 50I is equal to 30. Multiply everything by 10, because you remember for the linear equation, you want that derivative there for its coefficient to be 1. Right? So we have di over dt plus 500I is equal to 300. The integrating factor, mu, is equal to e to the integral of 500 dt. So we get e to the 500t. So we multiply to the left and the right side the integrating factor. The left side is automatically the derivative of the product of the integrating factor e to the 500t in the dependent variable, which is I. That's equal to the right side times the integrating factor. Take the derivative of both, take the integral of both sides, excuse me. So we get e to the 500t times I is equal to integrate that e to the 500t, you have to let u equal to 500t, and so then du comes out to be 500 dt. So basically you're going to have a factor of 1 over 500, right? So this is 300 over 500 times e to the 500t plus some constant. I integrated both sides. Mm-hmm. You want to be able to see it, because eventually you want to be able to do these problems without having to do some of the previous calculus, so you can kind of see what's going on. Let u, and better put here, this implies this is e to the 500t times I is equal to 300 times the integral of e to the 500t dt. So let u equal to that 500t. That implies that du is equal to 500 dt. You need to represent dt in the integrand, but dt from this substitution is du over 500. Right? So this implies that 1 over 500 du is equal to dt. So I'm going to represent this dt with 1 over 500 du. So that left side is e to the 500t times I is equal to 300 over 300 over 500 times the integral of e to the u du. And that's just 3 over 5 times e to the, that u was 500t. Plus some constant. Some of you on the test, you left off your constants and just threw you off. So remember, the big chunk of the solution in terms of taking limits comes off of that that factor of c. So you want to, don't leave that off. That's important. So looking at this is equal to this. So if you divide both sides by e to the 500t, then I get I of t is equal to something over there. Right? So I of t is equal to 3 over 5. I'm dividing by e to the 500t plus c times e to the negative 500t. Now that problem, he gives us the initial condition. If the current represented by I is 0 at time equal to 0. So for I of 0 equal to 0, that implies that 0 is equal to 3 over 5 plus c times e to the 0. And you get from here that c is equal to negative 3 over 5. So I of t is equal to 3/5 minus 3/5 times e to the negative 500t. Now deduce Ohm's law by taking the limit of the current. So the limit of I of t as t goes to infinity is equal to the limit as t goes to infinity of 3 over 5 minus 3 over 5 times e to the negative 500t. Now, as t goes to infinity, e to the negative 500t goes to 0, right? Do you see that? Because he's really downstairs, right? It's really 1 over e to the 500t. So as t enlarges, over e to the 500t goes to 0. So all you have left, the limit of a constant is a constant. So all you have left is 3 over 5. That's equal to I. That's Ohm's law. Here, I is equal to E over R. But here, E is 300 volts, right? And R is the 50 ohms. That is Ohm's law. Right? Now understand that everything that you deal with in physics starts with us. Huh? I know. I know. But the power behind mathematical science is the limit. Understand that the limit was hidden in algebra. Didn't talk about it, but it was there. Because you can't have that exponential formula P equal to C times e to the kt unless you deal with some type of derivative. And isn't the definition of a derivative a limit? That's all it is. Right? It starts with us. Mathematics is the mother of all science. The last problem, and then I'll be out to hair. So how high, if there's no air resistance, this is very easy if there's no air resistance. The next problem deals with air resistance. Suppose a small cannonball weighing 16 pounds is shot vertically upward, as shown in the figure, with gravity being pulled on it, with the initial velocity here of 300 feet per second. The answer to the question, how high does the cannonball go, depends on whether we take air resistance into account. We do that to get an idea of what's happening. In actuality, what we get here in this problem is not true, because by all means, air resistance does take place with objects in the air. But we get an idea of what the answer ought to be, and the answer is typically it's kind of close to this, just depending on air, the air factor itself, the resistance of air. How much is that? Suppose air resistance is ignored. If the positive direction is upward, then a model for the state of the cannonball is given by this second derivative is equal to negative the acceleration due to gravity. Since we know that the derivative of the space movement divided by time gives us velocity, distance divided by time. So here, the last differential equation is the same as dv over dt is equal to negative g. We take g to be 32 feet per second square. Find the velocity, v of t of the cannonball at time t, and then use the result obtained in part A to determine the height of the cannonball measured from ground level. Find the maximum height attained by the cannonball. So we start with this. that dv over dt is equal to negative 32. Just separate the variable, so we get dv is equal to negative 32 dt. Integrate both sides, and this implies that integral of dv is equal to negative 32 integral dt. So I get v is equal to negative 32t plus a constant. The constant is the initial velocity. We're looking for height, right? So the height would be that s movement, right? So here, if I integrate this again, integrate the velocity, that would give me the distance equation. So here, the integral of v dt, so that gives us s, is equal to the integral of negative 32t. Look, by the way, this initial velocity, he gave that to us to be 300, I believe. It was somewhere there. There it is. See that? So the initial velocity is 300. So this is plus 300 dt. So here we have s is equal to negative 16 t squared plus 30t. It would be plus some constant, but the constant at the initial point is said to be at ground level. It's assumed. So here the initial plus c sub 1, if you will, would be 0. So we're here. Now, this motion equation, s equal to negative 16 t squared plus 30t, is an upside down parabola, right? As a matter of fact, this is the shape of it. So if I set s equal to 0, then that gives me when this ball is thrown up and then when it comes back down here for the distance or the measurement to be back at 0, at rest again. Right? Yes. Yes, sir. Yep. S represents the position. Okay. So setting s equal to 0, we solve for the total time. There's 2 times that s is 0, right? At the beginning, and then when it comes back down. It goes up and it comes back down, right? So doing that, s equal to 0 implies that negative 16t squared plus 300t equal to 0. Well, the first here, there's 0, we factor it out, so we get negative 16t plus 300 equal to 0. T is equal to 300 divided by 16. And that gives you, has anybody get that? It's like 18 point something. $18.75. Well, this parabola that we have is a perfect parabola, right? So half of this time would give us the time at the height. See that? If I split it in half. Right? So here, at this time, t is 18.75. If I take half of that, I get t equal to 9.375 seconds. So if that be the case, then I have S is equal to negative 16 t squared plus 300 t. The height is at t equal to 9.375 seconds. So S is equal to negative 16 times 9.375 squared plus 300 times 9.375. Anybody calculate that? You get 1,006.25. I'm sorry, 1,406.25 feet. Yep, 1,406.25. Okay. So now, the rest of the problems that I've assigned, some of these problems were homework problems that I've done. This will help you solve the problems in WebAssign. And if there's one or two problems that I did not do in the book, by all means, you definitely want to go back and do that. And here's what I would do if I were you. The problems that I have done, you go back and work them yourself. At least you do have a study guide based on what I've already done. And so I think the more you do it, the more you become familiar with the information. Thank you.